There we go. Welcome to SF Pug August Meetup. I'm Catherine Saar, your host. Before we begin, the meeting is being recorded and will be posted on YouTube afterwards. Everyone who speaks during today's event will be part of the recording. We will do a Q&A at the end of the presentation. If you choose to ask a question, your voice and image, if you have your camera on while speaking, will be part of the recording. If you do not ask a question, you will not be part of the recording. If you're using the most recent version of the app, which we do recommend, you can use the raise hand function to join the queue. If you are using an older version of the app which does not have this function, please use the chat to let the organizers know you would like to ask a question, and they will add you to the queue. The organizer will let you know when you are next in the queue, so you can be ready to unmute your microphone and ask your question. If you do not want to be part of the recording, the organizers can convey your question to the speaker. In that case, please type out your question in full and let the organizers know you would like them to present it to the speaker. If you have any technical issues, please message the organizers for assistance. If you drop out of the meeting and are unable to rejoin, you can post a message on the event meetup page, which we're monitoring during the presentation. SF Pug, Bay Area Postgres, is a PGUS affiliated user group, and I am a volunteer for PGUS. SF Pug is sponsored by PGX, and I work for PGX. Without further ado, here is Adam Furmanek with OpenTelemetry databases and machine learning. Troubleshoot like a pro.
Hello, everyone. I'd love to begin, but I can't share my slides yet. Oh, I think I can now.
Try now.
Yeah, hope it works.
Perfect.
Okay, let's begin then. So thank you, Catherine, for introducing me. Hello, everyone. My name is Adam Furmanek. I'm actually dialing in from Poland, Central Europe, so it's something like 9 p.m. my time, so good evening. And hey, everyone, and for the next 60-something minutes, we're going to talk about OpenTelemetry, databases, machine learning, and other stuff, mostly focusing on Postgres, although what I'm going to share will be or is applicable to generally any database, no matter actually whether it's SQL or NoSQL. What we're going to go through is we will try to answer or maybe find a solution for the problems that we face every day, for how to debug and troubleshoot applications efficiently, especially in the modern world when it's not that we have monolithic app with one database, but we do have much more complex scenarios, more applications, containers, cloud native apps, and other stuff. And it's sometimes very hard to figure out how to reason about the database, about the performance, correctness of our queries, how to optimize them, and how to troubleshoot issues as we go along the way. So we are going to discuss what problems we may face and how to tackle them. And we are going to use OpenTelemetry for doing that. We'll focus on solutions that work with Postgres, and ultimately we'll also land in the world of AI, and we are going to use machine learning to skyrocket our experience. That's the idea. And as it was already mentioned, feel free to wait with your questions until the Q&A session at the very end, but I'm also following the chat here, so if you happen to pose a question, I hope to not miss it, and we can answer those questions as we go. And also, just a note, I work as a dev role in a company called Metis. I will briefly mention what we do at the very end, but just keep in mind that what I'm telling you is mostly about the databases and the knowledge and the open source stuff, but also at the very end, I will show a couple of screens that may be interesting from you that come from a product. Being that said, let's go. So the agenda, we're going to start by discussing what breaks today, which things are actually flaky, and what may pose issues in the database world. Then we are going to consider, okay, what do we need to make the world easier, to troubleshoot better, and to fix all the problems that we are facing. And finally, we are going to build it. We are going to see how to build the solution, namely database guardrails, and we are going to see how to introduce them in the organizations and wire them up in your apps. So let's go. So what happened? Let's start by going through a little piece of history. As I already mentioned, the world today is much more complex than it used to be. Like 15 years ago, our applications were quite straightforward, right? We had something like one application that was basically running on like a couple hosts, maybe with load balancer, and one database, typically SQL database, right? If we were to scale out to do more, build more applications or whatever, we typically just copied that on the side, and we had a completely independent environment that was following the same principles, right? This is how we were implementing applications years back. Unfortunately, or fortunately, depending on how you look at the thing, the world has changed significantly. We do not work with monolithical apps anymore. We do not work with just like a couple of hosts and one database. No, the world today is much more complex. First, we have many databases for each of our applications. So it's normal now that one application connects to multiple data sources, especially when we are doing things like domain-driven design, CQRS, when we are like separating our bounded context to keep data independent. We have the same entity replicated across multiple databases and even like shredded with different attributes to better suit the needs in various places of our ecosystem, right? This is normal nowadays. Another thingy that we should be aware of is we have various database technologies, right? We do have SQL databases, but we have NoSQL databases as well. We have databases for like OLTP, which is like transactional processing, but we also have OLAP databases. Often, we even go for hybrid approaches like HTAP. So we have hybrid transactional analytical processing systems, and we would like to serve all of them from maybe one system or maybe from multiple databases. We deploy like local databases, on-prem databases. We deploy cloud solutions like RDS or Azure Document DB and whatever, or Cosmos DB, or we even deploy databases that run in memory. Right, so we have solutions that can do analytical in memory, or we even go with like BDTOs that do all of that with like hundreds of gigs of RAM to make it more performant. We also have things that are like serverless, right? We have Lambdas, we have serverless applications, low-code, no-code solutions, and most importantly, all those components that we deploy, they talk to each other. So we have queues, we have SQSs, we have enterprise buses, we have storage that we use to share the data, we have databases that can be used just like regular SQL databases, or maybe like queues that connect things between. We use RPCs, we use regular like REST APIs, many different things. So all those things are now very chatty and talking to each other. And this is normal for us, that the deployment is severely decoupled, meaning that it's not that we process the application in one go. No, we deploy each component separately. We can scale them out separately. We use Kubernetes, we use cloud native apps for doing all of that. And so whenever there is a problem, things get much more complex. Previously, like years back, when there was a problem, then it was rather easy to figure out where the problem could be. It could have been like either in the application or in the database, right? Because simply there was nothing else around. But today, it can be literally anywhere in this ecosystem. It can be in any component, any database, any serverless solution, any pod, any Kubernetes instance, whatever. And if we are to debug what's going on, then it becomes very tedious. Why is that? That is because our logs are now scattered and distributed. It's not that we have just one log file. No, we have logs from queues, from databases, from applications. We have things that talk with each other across the globe, and it's super hard to reason what's actually going on. So we had to, during this DevOps, we had to learn how to deal with the applications that we wanted to deploy often and modify often. And we learned how to do DevOps well. We learned how to deploy stuff. We learned how to build applications so they are scalable. We learned how to go with Kubernetes and other stuff. So now we can easily scale out or scale up or whatever and deploy many times a day. However, when it comes to troubleshooting, especially troubleshooting performance related to databases, we do not have good solutions. You may be wondering why I'm saying that, because, well, we do have solutions like dashboards and monitoring, right? But there is a problem with dashboard. There are actually many problems. Like if you take any dashboard, any metric monitoring solution of yours, something like Dynatrace, AppDynamics, even like CloudWatch in AWS or whatever, all those solutions, they always strive for bringing as much data as possible. They are actually pretty good at bringing like multiple metrics from CPU, memory infrastructure, networking, JVM runtime, whatever else, garbage collector, L1, L2, L3 caches in CPU and whatnot. They can grab all those metrics and literally swamp us with the data. The problem is we don't know what to do with that. I mean, sure, we can bring the data, we can even build like fancy charts, pie charts, trend lines, or whatever, but at the very end of the day, we have no idea what's going on. I mean, we see there is a problem. We see there is a fire burning, and we may even be able to point where it burns, but we don't know what caused it. We don't know how it happened and where it started. And most importantly, we don't know what to do with it, how to put this fire out, how to fix it, right? And this is what we are going to tackle during this presentation. We are going to understand how to deal with this distributed world and how to troubleshoot all these things around, focusing on databases, but generally applicable to all the distributed systems, and how to do it efficiently. And it's important to understand that it applies to no matter what company you work for. No matter whether you work for like small startup with a couple of people on the board, or maybe for like big Fortune 500 enterprise, doesn't matter. The world won't be any easier. It will only go more and more complex. And no matter what we do, we are going to face this complexity. So let's see what we can do. And in order to understand how to fix the issues, we need to understand what breaks in today's world. We need to understand how things break and what problems we are going to solve. So let's go through some of them. So technically, whenever we are talking about database issues, they can all be more or less grouped in one of the three areas that we see on the slide here. So the very first area is code changes, meaning that we modified the code of our application and now something breaks. So we modified the code, like we start sending different SQL queries, bringing more columns, or using tables, views, or bringing in different data source. Those issues are generally relatively easy to troubleshoot, meaning that we often catch those issues during the development just because, hey, we are touching the code, right? We are touching the SQL queries that we execute, so we can see what's breaking, what's changing, and whether we are getting the correct result, right? The other area of issues that we may have is anything that is related to changing schemas, meaning that we add tables, add columns, change data types, do other stuff around how we store the data physically. Again, issues around that we kind of can catch. They are a little they are a little harder to catch. That is because whenever we actually test our applications, we just run all the schema migrations, and we do not verify those schema migrations as they go. We only verify whether we landed in the state, the end state, and we consider it correct. This is, most of the times, this is good enough. However, if the schema migration is slow, for whatever reason, we will find issues and we'll face issues when we deploy this to production. We'll discuss that a little bit later. However, there is third big area of issues, of errors that we face, and this area is something that we literally miss. We are blind to that. And this area, I called it here query changes. And I'm not talking about that we change the SQL statement that we execute. No, I am talking about the case that we send or execute exactly the same query as we used to for the last months, and yet this query changes somehow. It stops using an index. It becomes slower. Statistics got out of date. Maybe we changed the partitioning key. Maybe something else happened. And this query is now becoming way slower and causes issues that we are yet to find out in like various places, just because obviously one database may like impact all the ecosystem that we are dealing with. And the biggest issue in this area is that our testing procedures, they do not capture issues, don't find those issues during the development. How is that possible? Well, whenever we run unit tests or generally testing of more or less any kind, we are typically focused on the correctness of the data. We only verify whether the data that we read from the database or that we write to the database is correct, whether we get the correct entities. We rarely verify whether we read those entities in an efficient manner, whether we read them fast enough, and whether this is going to scale well in the production system. We do have load tests that try to address just a bit of the problem, and we are going to see later why that's not enough. However, the biggest issue I want to stress here is we simply do not verify how our queries execute. And let's now see what can break when we are talking about how queries execute. So the very first example that actually comes from one of the production systems I was working with is the code you can see here on the screen. So we have some code running in the application that is trying to get the user table and joins many tables, for instance, user details, some text associated with user peers, etc., etc. This is actually coming from one of my production systems, and it generated this SQL statement behind the thing. This SQL statement was generated by the ORM, so the mapper that did it automatically, and we can see that we have many joined tables in this single query, right? And if we now run this in production, then this single query was reading something like 300,000 rows, or actually returning 300,000 rows, and this whole piece of code was running for 25 seconds. Why is that the case? Well, it's rather easy to understand why that's the case. That is because we have this many joins. So we exponentially increase the number of entities that we return from the database and that our ORM needs to then translate into one big object in the application code. What's worse, we also duplicate most of the data just because, well, we are joining and exponentially increasing the number of rows. And we also bring columns like over and over again that we don't need. So this is something that, well, it was immediately seen when it's been deployed to production. How did it happen that it was missed during the development? Well, if your database is small in your testing procedures, and that's typically the case, whenever we run unit tests, we are dealing with the database that has what, a couple of rows, maybe 100 of them. So you won't see any problems even with this exponential increase, because it's going to generate a couple thousand rows, which will be very fast, still very fast. That was the problem. Unit tests, they focused on the correctness of the data, but completely disregarded how the query was executed and whether it would be fast enough after deploying to production. How could we fix that? How did I fix that in this particular case? Well, the fix was rather straightforward. Instead of running one query, I sent many queries for each table separately, and then I merged all those objects in the application code. And you may wonder how it happens that it's faster, because, well, instead of running one query, I was sending something like 7 or 8 queries. database, right? It was still faster because we avoided this exponential increase in the number of entities. Each of these queries were getting something like maybe one row in total, or maybe a couple of them, using index, which was rather fast and efficient. Effectively, this was much more efficient, and well, even though it was many queries, it was still running way, way faster. I'm talking about like milliseconds here instead of 25 seconds. So that's one example of what can go wrong with databases when we are talking about this problem. It's like we don't see what query gets generated behind the scenes, and we completely disregard performance. But we can take other examples as well. For instance, imagine a programmer that wanted to increase the readability of the code, make the code cleaner or whatever. So we have this table that is called boarding passes. It has something like 8 million rows. And what we start with is we send the query that wants to basically get the ticket number from the boarding passes. And this query is just shown here to, show the principle, not necessarily something coming from actual production system. So we get the boarding passes, we join this table like 3 times, then we get the ticket number, calculate like double hash of it, so we calculate the checksum of the ticket number twice, and then we, do some filtering based on some value. Doesn't matter what value, etc., etc. What matters here is that we do this join 3 times and that we calculate this checksum twice. So you can see there is a bit of repetition in this query, right? First, I had to put this literal value 3 times here. I also joined this boarding passes, etc., etc. So the programmer may step in and think to themselves, okay, I can avoid some of this repetition, some of this duplication by using common table expression, CTE for short. CTE is basically like a temporary table that lives only during the execution of the query. So we basically create a CTE that calculates this double checksum of the ticket number, and then we basically join this CTE 3 times and try to do something with it here. So what we were effectively doing, we basically avoided calculating this double checksum of this ticket number in the filtering part. We do it in the CTE. The problem with this approach, even though it's more readable, the problem is the performance again. So the original query took 8 seconds to complete on this database, whereas the new query, more readable one, takes 13 seconds to complete. So this is nearly twice as long. So by changing the query, by improving its readability, avoiding duplication and whatnot, we destroyed the performance. And once again, the problem here is that our unit tests won't catch this issue at all. Why? Because we didn't change what data we get from the database. We didn't change the result. What we changed, though, is how we extract the result, and this broke the performance of this query, and something that we completely missed during testing. Yet another problem that we may face is anything that is related to changes in schemas, right? We may add new columns, and if we run queries like select star, then those new columns will cause higher network usage, higher obviously CPU usage, and we will just keep bringing more and more data, higher disk activity, higher IO activity, and whatnot. Not to mention that adding columns, changing their data types or whatever, may lead to table reorganization. That is because database engine may not be able to add this column inside the existing data. It may need to copy the table on the side, add this column, and then bring the data back. So this is basically table rewrite. And this table rewrite is, again, something that we won't notice when we are testing stuff locally. When we are testing stuff with small local database where we have nearly no data, then even if we need to rewrite all the tables, then it's gonna take what? A split second, right? But once we go to production, such as schema change may cause outage that takes minutes, hours, or even days. And I've seen companies where they were running migration like this for days because they were, well, taking quite a long time. So it's okay if we are aware that this will take hours to complete, but quite often we may be surprised that this schema change is taking way too long, way longer than we expected. And the worst part here is we just can't stop this schema migration. It either goes to the very end, or if we stop it, then, well, we just need to start rolling things back. And this may also cause tremendous performance degradation. Other things like dropping column, changing column types, or whatever, they obviously have similar effect, right? Dropping columns is actually a story on its own, and we could have a like 1 hour hour-long conversation just discussing how to drop columns from the database. The point here is doing any schema modification may break performance and may take our system down for a prolonged time. Yet another thingy is obviously our databases may be slow because, well, we don't have indexes, right? So there are various types of indexes like regular binary trees, indexes based on hash, on gene, vector indexes, vector databases, whatever, generally tons of different access methods, especially in Postgres, where it is pretty like all the indexes, they share very nice abstraction layer, and it's easy to add more and more indexes, especially for new and different data types that we can create on the fly. However, those indexes, again, they pose a problem. Why? Because the query will return the same result no matter whether we use the index or not. I mean, up to the ordering of the entities, but the content of the entities is going to be the same. So we won't see that there is a problem that the index is not used anymore because we only focus on the correctness of the data. However, indexes, they bring yet another challenge. If you take any junior developer and tell them, hey, if you have a performance issue, you can always think whether it's possible to add an index to improve the performance. And what we end up with is indexes everywhere, and we know that, right? Indexes are not free. Yes, they do improve the performance of read queries, select statements, and whatnot. But at the same time, they decrease the performance of data modifications, because now we need to modify the data in the table where it's stored and also in the indexes that are created on this table. So generally, adding more indexes may improve one place where we are actually trying to optimize stuff or whatever, and may break, at the same time, break the performance somewhere else. And again, our testing procedures won't capture that. Moving on, this is yet another problem with databases that we quite often disregard. Sorry, is there a question? No, okay. There is yet another problem about the bugs in our databases. We are quite used to the case that, well, our databases work well, right? But if we take isolation levels into consideration, we may be surprised how many things may actually break or how many unexpected results we may get. But if we are talking about databases that are supposed to be very scalable, databases like distributed databases, NoSQL databases, we may face yet another issue with those. And especially those issues are how those databases are implemented. For instance, one of the very popular bug or famous bug was called Halloween problem. Imagine that you are just running a query like this here, and you basically want to give a pay rise to all the employees. So you update employees, and you update the salary by increasing it by 10% for all the employees where salary is like below 10,000. Okay, and this query, the problem comes from the company that actually tried running such a query on the Halloween, and they figured out that, hey, this query may cause a problem because if your database is not preventing the same records to be edited many times inside one statement, then you may end up in actually giving way higher pay rise than you would expect. Imagine a case that all the entities are ordered based on the salary. If you now go through the entities one by one, you find some entity that is like below 10,000, like salary is below 10,000. So you update this salary, and now this entity goes down the list, right? Because it changes where it's stored on the like physical layer. So you carry on going through the entities, and then you find another entity. I mean, it's the same entity that you already modified, but you find it for the second time, you check whether the salary is still below 10,000, and it is. So I think you lost me for a second, but I hope I'm back now. Let me know if there are any troubles. But anyway, coming back to the topic, if we are now considering distributed databases like NoSQL for highly distributed systems, there are tons of bugs and databases can lose the data. There is a very nice project that is called Jepsen, and it was focusing on finding issues in distributed systems, for instance, in distributed databases like Mongo or whatever. And it was actually pretty nice to figure out how many bugs there are in all those databases. So no matter what database you use, always be a little bit suspicious whether like those things are, you know, correct, or whether, especially in distributed world, whether they give proper results. Moving on, there may be many more problems that are brought by the ORMs. One of the obvious problems that I will simply go through is obviously the n+1 selects issue. So imagine that we have a table called aircrafts that is in one-to-many relation with table seats. If you now implement a code like this, that you want to get the aircrafts and then you iterate over all the aircrafts, and for each aircraft you want to get the number of the seats, then behind the scenes, this may generate n+1 queries. It will generate one query to get all the aircrafts, and then it will generate n additional queries for each aircraft to get the number of seats. And fortunately enough, this issue can be easily solved by changing our ORM configuration from running queries like in the lazy mode into the eager mode. So we do not run them lazily, we do not run them like one by one, but we try to bring the data as early as possible. So this is something that, well, it's very simple to change we can change it easily in the configuration. The problem again is unit tests won't capture this difference, because from the correctness perspective, it doesn't matter whether we go with one query or n+1 queries, the result is the same. But we might think, okay, if we know there is an n+1 problem, why don't we just change the ORM to always go with eager queries and never use lazy loading? Okay, and if we do that, then we end up with the situation just like we had before. We get the user repository, we get the entity for that, and then we end up with one enormous query that brings like hundreds of thousands of entities just to build this one user object. Unfortunately, we can't just go either or. We can't just enable like everything to be eager or everything to be lazy. No, we need to consider each query or each code path separately, and once again, it's not clear what happens behind the scenes. ORMs, they bring more and more issues, actually around, for instance, polymorphism. If we just take the regular object-oriented programming and put it on the database just like that, then our ORMs will deal with that because they have plenty of patterns, for instance, table per hierarchy, table per concrete class, or whatever else. The problem with those approaches, though, is that they break the performance. Why? Because now we either need to query multiple tables, or we need to duplicate attributes, or do other magic just to keep the correctness. This is called impedance mismatch, where we try to put the object-oriented programming world on the database world, and those worlds are different. ORMs bring, for instance, yet another issue around that. Imagine that we would like to keep some complex data in the database. For instance, we don't even need to have complex data. Let's talk strings and varchars. In typical programming languages, like let's call it Java, C#, JavaScript, whatever, we have just one type that represents the text. It's typically string. right? However, in the database world, we may have different configuration of the text type. We may have different collation, which is basically different ordering of characters, or we may compare strings differently. We may ignore the casing of letters, or we may do something different. We may ignore like national characters or whatever else. This is something that we can't represent in the OOP world in Java or C# or whatever else. And this gets even more complex when we are talking about heterogeneous applications. Imagine that one database is used by both JavaScript, C# or whatever, and like a couple other applications. How do we know if all those applications are dealing with the data type in the same way? And what if, for instance, we are talking about like spatial data? Is it encoded as like two doubles? So basically something like 128 bits of data? Or is it like encoded as a string representing a tuple, a pair of numbers? In the latter, it will be way slower and will cause performance impacts, right? So those are the issues that ORMs bring, but there is way more to that. And I won't be going much into detail. We can just quickly mention that, hey, what about transaction isolation level? Do you know what's your default isolation level in the application or in the ORM of your choice? Who starts the transactions? Do you have caching? How does cache work when you are dealing with transactions and rollbacks? What about connection pooling? What about query hints? What about like migrations? Who controls the migrations? Does your ORM enforce the specific schema on the table? What happens if your ORM recognizes, oh snap, the schema in the database is actually different than what it has in the source, right? Those are the problems that we face with ORMs, and the problem is always about changes are in various places, they are hidden from us, and our unit tests do not catch those issues at all. So we've seen plenty of examples how things break. So let's now start thinking, okay, how can we fix them? How can we make the world easier? And how can we reason about that stuff to avoid all those issues and never deploy faulty code to production? So the very first thing you may think of, okay, let's do testing. But as I already mentioned many times during this talk, unit tests, integration tests, end-to-end tests, all those tests, they focus on the data correctness. They do not verify how we execute the query. They only verify whether the query gets the proper data or whether we write correct entities to the database. They do not verify whether we use indexes, which indexes, how often, etc., etc. They do not verify statistics, nothing like that. And also, when we are talking, for instance, about schema migration, we always, or nearly always, run the tests after we already migrated the database, meaning that we do not run the test during the migration. So we very, very rarely run our code and verify how it's going to work when the schema is just different or something breaks or whatever, right? We just run those schema migrations, we wait for them to complete, and then we start running tests, okay? So those tests won't ever catch the issues. But you may say that, okay, we have load tests, right? Why isn't load testing a solution? Many issues, many problems with load testing. Let's start with the cost. First, it takes hours to complete a proper load testing. That depends obviously on your application, on the company you work for, but it's not uncommon to see load testing running for 6 hours, 8 hours, 12 hours, especially when we take caching or tiered compilation or, warming up other environments before even starting the load tests or increasing the traffic during the test. Generally, load tests are pretty expensive to execute. Not to mention that whenever we run those load tests, we typically run them in some external environment, like pre-production environment or whatever. So we simply let them go, and then we come back to the office the next day, and this is when we check the results. So if something breaks during the load test, then effectively we waste 1 day of work. Yet another problem is, how can we actually implement those load tests? We need to deal with data distribution, with anonymizing the data, with GDPR, with California Protection Act, with other stuff that prevents us from, taking the data from the production system and just running it in pre-production. And this affects what we get from the load tests, because if we do not have proper data distribution, then effectively we may be testing like our application with the traffic from the US only. And then we deploy it to production and hey, we have quite a big traffic from European Union, right? But it wasn't represented well enough in the load tests. Another issue is we may completely disregard some smaller countries because they bring something like 0.1% of the traffic, right? So those things are really hard to replicate. Things are even worse when our application is stateful. For instance, what if our application needs some, like in order to call some API, we need to prepare the data, create the user beforehand, documents, add the data or whatever. We can't simply take the requests from production and start shooting them at the non-production environment. It just won't work. The data will be like garbage in, garbage out, right? Yet another issue is what about the hardware and money that we just need to pay? Like, imagine that we are load testing something that requires machine learning, right? We need to have GPU-enabled machines or TPU-enabled machines or whatever. Those machines are first super expensive, and second, cloud providers can't give you those machines just like that. If you ask for hundreds of those machines, cloud providers will just tell you, no, we don't have those. You need to wait for hours, right? So we can't run the load tests. But most importantly, all the issues I mentioned about load tests, well, we can sort of deal and live with them. The biggest issue we have with load tests is that they happen way too late in the development pipeline. We run load tests after we already designed the solution, implemented it, reviewed it with our peers, merged into the code base, and deployed to some pre-production environment. This is when we run our load tests. So if those load tests find issues of any kind, then guess what? We need to come back to the whiteboard and start again from scratch. This takes an enormous amount of time. It is effectively super expensive because we need to implement everything again, not to mention that it brings frustration and generally is not very nice when we want to plan our roadmaps reliably. So this is the biggest issue. We can catch some of the issues like by using load tests, but it happens far too late in the SDLC and our CI/CD pipelines. Okay, so what can we do then? Well, we need to figure out how to deal with those problems that we mentioned before. We need to understand whether we are using right solutions, so whether we are using proper indexes, whether we have good queries, whether we have ORM configured properly, whether we use like proper databases. And we need to also understand or check whether we implemented our solutions correctly, whether we have statistics up to date, whether we have we are vacuuming our databases, whether we don't have the fragmentation, whether fragmentation, whether we have indexes in place or whatever, whether our application scales and whatnot. Those are so many things that are super hard to reason. And let's now see how we can tackle all of them. And the solution to all of them is database guardrails. So what we would like to do is we would like to basically bring the context of what is going on in our ecosystem to reason about what is going to change in the production to prevent the bad code from being deployed to production, automatically find the issues, automatically fix them, and troubleshoot them as easily as possible. So the idea here is we would like to build a big proper observability 2.0 in our ecosystem to see what's going on. So before diving into details, what is observability 2.0, we need to understand what we have typically when we are talking about monitoring and other stuff. So it all started with telemetry. telemetry was basically the ability to collect the data from our systems, collect like logs, metrics, traces, whatever else. We didn't like telemetry initially. However, nowadays telemetry is quite common. We have well-defined standards, well-defined libraries for that. So telemetry is everywhere. Like, sure, we can say that we don't like it, but the reality is telemetry is now everywhere in our operating systems, applications, databases, networking, whatever else. So telemetry is just the ability to collect the data, to collect those signals. Once we have a telemetry in all the places, meaning we have telemetry in our database, in our application code, in our networking, in our operating system, in our queues, service buses, whatever else, we get the visibility. And visibility is basically the ability to see what in every part of the system, in every piece, in every component of our ecosystem, of our environment. Once we have this visibility, we can start tracking it, monitoring it automatically. And this is called APM, Application Performance Management. So this is basically when we build a solution or bring in any solution like New Relic, Datadog, whatever else, that basically extracts all those signals and constantly monitors whether we cross some thresholds, whether metrics spike or whatever else. This is APM. However, APM and generally any monitoring solution, they only focus on bringing the data and showing them to you and asking you, hey, you go figure what to do with that. And observability is about reasoning about all of that and giving you answers instead of giving you the data to do the reasoning. So monitoring is about like we bring the raw data, we bring raw metrics, we focus on the infrastructure, JVM, runtimes, whatever else. We just bring all that we have, put in one place, build nice charts, build nice graphs, whatever, give you some ability to configure alarms, to set thresholds, and page you at night when things break. Observability, on the other hand, is about taking all of the data and reasoning on what's going on and giving you solutions. Instead of giving you the data points, showing you that, hey, your CPU usage spikes, observability is about telling you, hey, you deployed this code change last Wednesday. Today is Saturday, it's evening, you have more clients coming to your website. Now the query that you changed on Wednesday stopped using an index, and this causes your CPU go up. If you want to fix it, you need to configure the index. This is what observability brings. Observability wants to connect the dots and give us this, show us this interconnection of all the pieces together to answer all the questions and fix all the problems that we may have. How do we build it? Well, in order to build it, we need to understand what to observe, how to observe it, and finally how to automate all of that. So whenever we are talking about databases, we need to understand how queries are executed, right? And whenever we execute a query, no matter whether it's Postgres or any other database, a query typically goes through various stages executed or performed by the database engine. And one of the stages is called planning. And planning is basically the case when the database engine takes the query and generates many physical plans how we can get the data, which indexes to use, in which order to join the tables, whether to store some data on the drive or calculate it on the fly or use temporary tables or whatever else. This is planning. So what planning does is we can take the query, basically any query, and we can ask the database engine, hey, explain how you are going to execute such a query. And the database engine will give us something that is called a query plan. And if we now try to understand this query plan, we'll quickly notice that first, it consists of multiple nodes, and those nodes, they represent physical operations that are executed by the database, meaning we scan the table, or maybe we extract the rows using an index, or maybe we sort the data, or maybe we store it on the side in the file to keep it pre-calculated or calculated once to use it later on. And each node in the query plan explains what's going on, and most importantly, it explains the cost of this operation. And cost is more or less a meaningless value that we shouldn't attach ourselves too much, because this value doesn't give us any, we can't translate it easily to number of seconds or maybe number of megabytes transferred from the disk or something. Stage of the query plan. This value is calculated based on some heuristics, statistics, some hard-coded values like how hard it is or how expensive it is to get a single row from the table when we are scanning the table. So we basically have some constant numbers that we just put in just to do some math and then come up with a number, the ultimate number explaining the cost of the query. Now, what does it give us, this cost of a query? Well, the database engine can create multiple database, a query plans, showing different ways of how to execute the query. One query plan may use indexes, the other query plan may not use the indexes, yet another query plan may join the tables in different order, right? So we generate those query plans, we calculate the cost of each plan, and then we pick the cheapest one. We pick the cheapest plan because we assume it's going to be executed in the fastest way, right? This is the idea. And the important part here is we can generate such a query plan for every single query that we execute. So nothing stops us actually from integrating with the developer environment of our programmers in our teams and plug in tiny piece of logic that will capture their queries that they execute in unit tests or whatever, generate query plans for these queries using production statistic or production database, and then immediately check whether those queries will be fast enough or not. We will immediately see, once we project those queries onto the production database, we'll immediately see whether we use indexes or whether we are facing a table scan going right after we deploy to production. Now, how do we get those queries? How do we get those plans? And to do that, we can use OpenTelemetry. OpenTelemetry is basically an open standard that allows us to integrate the telemetry into basically any application we can think of. Databases, C#, Java, any language, queues, whatever else. We get the SDKs and libraries from OpenTelemetry that let us collect things like logs, traces, metrics, and other thingies. So OpenTelemetry is basically now an open source standard for building those SDKs and those libraries that capture those various signals. So basically, OpenTelemetry is from our coding perspective, is an SDK that we just install into our application using, I don't know, pip install or maven install or whatever else. And this SDK plugs itself into ORMs, web servers, our runtime platforms, or whatever, and it captures traces, metrics, logs, and other stuff. So this is what OpenTelemetry does. Now, what it builds behind the scenes is it builds traces and spans, meaning that imagine that we have the environment in which we basically want to execute some workflow, like let's say buying a ticket, and the user sends a request to like a web server or a load balancer here. This load balancer calls another server that ultimately calls the database, emits some value to a queue, and then contacts some payment provider or whatever else. Once we have OpenTelemetry plugged into all of these pieces, we can build a trace that explains that how every part, every like node in this ecosystem, how it executed the operation. And this span is basically like a piece of data that explains like when the thing started, when they ended, what attributes we had, like HTTP, SQL query, whatever else, some human-friendly explanations, some other data that we added to all this stuff to enrich the things and whatnot. So this is how spans work, and this is how we can build traces out of those spans to reason about everything that was working here. So now, being that said, we know that queries are executed by the database engine and we can get query plans. We know we have OpenTelemetry that can plug itself into the applications of our choice. What we can do now is we can build a new modern observability 2.0 that will let us immediately prevent all the issues from happening in the production environment. How does it work? Well, we start with the developer writing the code. They work on the code in their development environment. They simply write the application code, touch the database, run some queries or whatever else. So they run application locally. We deploy the telemetry collector on the side by using OpenTelemetry that they just need to install into their application once, and that's it. And this telemetry collector extracts the queries from the ORM, from the application, and consults things how they are executed in the local database. So we can extract like parameters, query plans, whatever else, and ultimately we can store them into some centralized storage, right? We can do the same when doing when running things in our CI/CD pipeline. So our CI pipeline runs the application. We again have the telemetry collector that extracts data from the database and stores them in the centralized environment. But here comes the crucial part. Once we extract the data from the developer environment very early in the CI/CD, in the development pipeline, we can now project this data onto the production database. We can simply take the select statement that we executed locally and ask the production database, hey, explain how you are going to execute such a query in the production. And once we have that, we can immediately reason whether this query is going to be fast enough or if it's going to break. That is the idea. We can immediately capture all of that stuff and prevent the slow code from being deployed to production because we immediately see that we lack indexes or whatever else. What's more, we can also monitor our production application, like the very far right side of the CI/CD pipeline, monitor the production database, and constantly observe what is going on and how our things are actually working and how they evolve over time. This is to address all the issues and troubleshoot them automatically whenever they happen. So being that said, let's actually see that in action before actually going to ML. So I'll give you just a couple of screenshots from our platform, but obviously the other solutions that try to do the same, although they miss kind of the points, some of the points that we find very important. So for instance, I can now integrate, we can now integrate with the application of our choice, and we can say that, hey, this is the REST API that your application exposes. And this REST API, when it was called from unit test or whatever, it actually caused this SQL statement to be executed in the database. This is the visualization of the SQL statement, but most importantly, we can easily say, hey, those things won't be fast enough in production because we have table scans, because those things would read something like 40 million of data. They would, filter data inefficiently and whatever else. So we can very easily do all of that stuff and show you how those things are actually, like how they are going to behave in production. Similarly, we can integrate with like CI/CD. For instance, we can analyze schema migrations and show you that, hey, those are the schema migrations and those are the issues that we are having, okay? So this is just a glimpse of what we can do. I hope you now understand that by having this piece, we can now look into everything across the ecosystem. It's not like we are taking the monitoring solution that is just checking the metrics at the very end. No, we are taking the whole ecosystem, and even when things are just being developed very early in the pipeline, we can immediately see how they are going to work in the production. But we can take that even further. For instance, by capturing all the data from all the environments, from local environments, CI/CD pipelines, production, etc., we can now go and ask ChatGPT or whatever machine learning solution of our choice to optimize those queries. And for instance, we don't even need to be very sophisticated with that. How is that possible? This is conversation I had with ChatGPT, and you can see that I'm telling, hey, I have the following query that I just copied from the database, and how do I make it faster? And by the way, this is a big JSON explaining everything that I have in my database. Indexes, metrics, history of queries, whatever. You see, I don't even need to be very, gentle by providing, I don't know, clean data or whatever. No, I just bring this crazy JSON onto ChatGPT, and you can see that ChatGPT can figure out what's going on. It can find the indexes, find the patterns, suggest solutions. It can give you the solutions like, hey, you should create those indexes, and this is how you should rewrite the query, and other further tips. Obviously, depending on what ML solution you use and what data you bring, you may get various different effects. For instance, we can take this, obviously, I did it in a very rough way. I just put a big JSON of data here, right? But what we could do instead is we could bring some better prompting at this point. For instance, we could prompt the data and suggest that, hey, maybe it's better to change joins from this to something else. Maybe add limits, maybe use functions on the right side of the filters, maybe replace CTEs with something else, yada, yada, yada. We can bring in more data and build clever prompting solution that will not only use the raw data that we just bring from the JSON, but also some suggestions how to make those things better and how to make those things faster. So this is the idea what we can do. And this is there is a query on the chat. How does this relate to OpenTelemetry? Is it just that Metis agent happens to use auto network protocols to Metis cloud, or is there more to it? This is actually a very good question. When I was talking about the OpenTelemetry, what we actually use is, yes, we just use the OpenTelemetry to extract the data. There is no more magic to it. It's not like we extend OpenTelemetry, etc., or whatever. The only thing that is worth, that we should be aware of here is that OpenTelemetry is very generic. So we may want to, or we may need to extend the OpenTelemetry to extract some more details from the queries or from the applications, just because we know about those details because they are context specific. For instance, the default configuration of OpenTelemetry, and that depends on the programming language you have, the default configuration will not capture the SQL statement parameters. So if you do select star from table where ID equals black, then it won't extract this parameter value. It will give you question mark or something like that. So you may need to tune in those things to make them actually get the parameter values, so you can reason about those things better. And this is actually what we do, because we provide an OpenTelemetry collector based on the OpenTelemetry that actually extracts those parameters so we can reason about them in the production database better. But this is really just a very minor thingy. I mean, OpenTelemetry is the workhorse of this, and you can just bring in the OpenTelemetry and start reasoning about various stuff and extend it as we go. Coming back to where we finished, so I mentioned that we can start prompting the stuff. We can mention like joins, limits, etc., etc. But similarly, we can direct the engine to do different things about the schema. It's not only the changes that we do about the query, like change order of joins or whatever. We can add a different type of indexes. We can change stored procedures. Maybe we can even deal with triggers, or maybe just change the architecture of our application. What's more, we can even experiment with various machine learning models. For instance, I use ChatGPT, well, because ChatGPT is sort of the de facto standard, right, of how things go. But nothing stops you from deploying your local LLM. Like you can use CodeLlama, Dolphin, Mixtral, whatever other like machine learning models. You can feed them with the data of your choice, so it's safe, secure, never leaves your organization. You can prompt that with the things you understand about your applications, and you can enrich that with the things that you get from the OpenTelemetry or other solution capturing all of that. So this is the idea. What we can do. Before giving you a couple of more screenshots how this all can work together, there is yet another question in the chat, and the question is your custom auto collector that gets parameters open source and usable in any auto environments, or only works with Metis? It is open source. It can be used anywhere. You deploy it locally as a Docker container, and you are free to examine the code. However, at this point, it basically sends the data to the endpoint, which is like you would need to, if you were to use it with your custom endpoint, you would need to accept exactly the same schema, right? But effectively, yes, you can use it like locally. You can verify the source code. Whatever else, it's all open source. Being all of that said, let's see how all of that can work in action. We can, for instance, monitor your databases and focus on the database-oriented metrics. Apart from CPU, memory, yada, yada, we can, for instance, analyze tables and show you that, hey, those are the tables, those are the indexes, and bang, we have insights. For instance, you have many indexes, but you also have duplicate indexes, right? Maybe you should drop some of those indexes. Another thing we can do is we can, for instance, analyze indexes, how they are being used, right? Maybe this index wasn't used in the last 14 days, so maybe consider dropping it. We can analyze the schemas and give you ideas how things are interconnected with each other and how we can optimize all of that. And most importantly, we can analyze all the queries as they go through the database. For instance, we can see this is the query that is being executed. This is like the SQL statement. This is like general analysis of this query and like suggestions that it goes with table scan, you should add indexes, etc., etc. But we can also extract the execution plan, something that I was talking about, and then we can use ChatGPT or whatever other GPT solutions or Llama solutions to basically suggest how to improve that. For instance, you can see that your original code was this, like had cost of this, what, 30 million, but you can now use CTE to pre-compute the data and cost goes down. We can do other ideas. We can ask like machine learning solutions to come up with something like use derived table, include coalesce, and yada yada. So those are the things that we can build automatically for all those queries as we go. But we can also do the same for schemas, right? For instance, we can suggest and we can ask the machine learning solutions to suggest what indexes to build. We don't need to write like hard-coded heuristics or whatever. But then, because we are talking about Postgres, we can use HypoPG extension and verify whether this index is actually going to improve the solution, right? So we can then do something like this that we call index advisor, that we can easily tell you that, hey, in this database, we can improve the performance by 82% just by introducing indexes. And for instance, this is the index suggestion. Those are the queries that would benefit from this index, and you can simply optimize all of that. The next thing we can do is, how about we do all of that automatically? There is really no point in doing, in adding those indexes manually. If we wire up CI/CD into the game, we can simply submit automated pull requests and then simply ask the development team to approve them and get them deployed. So to sum up, databases may break for many reasons. We've seen that the world has evolved significantly over the last years, right? There are many issues that may happen, issues around performance, schema migrations, ORMs, configurations, transaction isolations level, etc., etc. But once we move to the observability 2.0, to the database guardrails, as we call them, we get the integration of everything along the way. We start the integration not on the very far right end of the ecosystem with solutions that only swamp you with the raw data points. We start the integration in the development environments, and we can extract what's going on there, project that onto the production database, and then reason about the stuff. And we can use basically multiple solutions that are out there. We can use OpenTelemetry to make things easier. We can deploy machine learning models. We can use ChatGPT to build this better focused monitoring that focuses on the database thing is, and that uses machine learning or any other solutions to basically prevent the bad code from reaching the production, or if something breaks, to troubleshoot things automatically. And being all of that said, I'd like to thank you for listening to this talk. Hope you liked it, hope you enjoyed it. And if you have any questions, feel free to ask them now. I'm happy to take them.
Do we have any more questions? That was a really good talk, Adam. Very straightforward and lots of information. Thank you so much.
Thank you for hosting me. It was a pleasure being here.
Excellent. We were glad to have you. That was great. Just a few announcements. And again, if anybody has any questions or comments, please feel free to put them in the chat. Thank you to PGUS and PGX. SF Bay Pug will be back on Tuesday, September 10th with automating Postgres index selection using constraint programming with Lucas Fiddle. Tuesday, October 8th, we will be presenting leveraging a PL REST extension to protect sensitive data in PostgreSQL with Sushant Rao and Rajan Palanoval. Upcoming conferences are PGConf NYC, September 30th through October 2nd in New York City, and PGEU, October 22nd through 25th in Athens. We will send a link by email when the video is ready, so watch our social media. You can find us on Twitter, LinkedIn, Mastodon, and Blue Sky by searching for Bay Area Postgres. We are looking for speakers for 2025. If you or someone you know is interested, please contact us. And it looks like Lata says, thank you, Adam, for the talk. May I please know if it's possible to access the slides for reference?
It is possible. I send you, Catherine, the slides. You can attach them to Meetup or wherever you find.
Perfect. Yeah, I'll post them in the comment section down at the bottom. That would be great. Thank you so much. All right. Any other questions?
Thank you, Odin.
All right, I think we're all set then. Thank you so much, everyone, for attending, and I hope everyone has a great rest of the day. Thanks, Adam.